Right. So first thing that we're gonna look at, and ever is the basics of whatever you're going to look at when it comes to math, especially in this course that is MAT 110, is sets, set theory, sets, what a set is, and just getting to understand those nitty-gritties. So today we'll just have a brief introduction. Next time we have class on Thursday, then we'll dive into more of the question handling of what involves a set. So if you have any questions at any point, just unmute yourself, speak, then I'll be able to attend to you. So number one here, we are looking at what is a set. So you need to understand what a set is. This is just simple. Imagine you having um, pens in your hands, and you have a green, you have a blue, you have a red, you have a black pen. You put them all together. That collection you have there is what we're calling a set. So now, what makes it qualify to be a set? So by definition, we're saying a set is a collection of distinct objects, and these objects we call elements. We're calling these objects elements or members of what? Of that set. So key things to always note about a set is that it is well defined. So if I'm talking about pens, I'm talking about pens. If I'm talking about numbers, I'm talking about numbers. And we'll specify, especially in this course, if we're talking about even numbers, if we're talking about integers, if we're talking about odd numbers, we are going to specify. So it has to be specific. Then we are saying that uh, the order in which the elements are listed does not really matter. When you have a set that is, let's say I have a set A, and this set is just 1, 2, 3, and I have a set A that is 3, 1, 2, 1. These are just the same thing. Even if I name it B, these sets are just going to be the same. And later on, we'll look at what makes a set to be equal to one another. But then we're just saying the order doesn't really matter. Though most cases we're going to list them according to ascending order, unlike descending order when it comes to the numbers and all. So and then we are saying that this set, or the elements that are in the set, have to appear only once in a set. So what do I mean? So when you have a set, for example, a set A, and set A has the elements 1, 1, and 2, and 3. So this 1, 1, 2, and 3, when we're writing it, we just write it as set 1, 2, and 3, because you having a repeating what is just going to be counted as one thing. So as one element, because you only have one element. In this case, because we're using one element, that's there. So this here is going to be counted as what? As one. So in short, what we are saying is that our set is not going to have repeating elements when we list them out. If I have a number, 2, it's going to be 2 listed out like that. I won't write two twos. Even if there were twos, I just count the 2 there, just like that. So that's what it means when we look at a set. And of course, we have these simple definitions here of what a set is. So we're saying a set of even numbers less than 10 is what they're telling us here. So less than 10 even numbers. Even numbers are just numbers that are divisible by 2, and they don't leave a remainder. So that is now, when I look at them, less than 10. So I'll start listing those numbers that are divisible by 2 but are less than 10. And then you see that I'm going to have 2, 2, 4, 6, 8. And these even numbers are coming from the natural numbers. That is, you're not considering any negative values here. Only positive values are being considered. Then on the other side here, they tell us a set of vowels. Set of vowels, the R, A, E, O, U. That's a set. It's well defined. I know what that is, So well defined, hinging on well defined. It's a collection because it has those letters there. A, E, I, O, and U are just a collection of letters, and we call them what? Vowels in the English alphabet. This is for the English alphabet. So you know from the definition that indeed this is going to qualify to be a set. Well, we move on to the two major things that we're going to look at in this class, which is representation of sets. So there are two main ways in which we can represent a set. Number one is what we call roster method. Roster method or tabular method. Roster or tabular method. So this is just a method of listing, or you could call it listing method. It's just a way in which we list these sets. So now, when you look at the following, we have this example. It says write the following in roster form. Or they would tell you list the following. But then how would we write this? So you look at the first one. The first one here, what we just have is they're saying A is equal to the set of OX such that X is a member of this N here, capital N, which you will see will represent like this. It just stands for natural numbers. So they're telling us that X is a natural number. So the numbers we're listing are natural numbers, one, and they're saying they're in between 50. So 50 and 60. So X is here, and then you have your 60 there. So it's in between here. And then when you look at the signs, you have less than or equal to on the left side. Then you only have a less than, strictly less than on the right side. So what that means is on the left, we have strictly 50 greater than an or equal to. So that means that 50 is going to be part of it because of the equal to part that's there. But then when you look at the right side where we only have 60, 60 is, there's only a strictly less than symbol there, meaning that 60 is not going to be part of what of our listing. So if we're to list the natural numbers, so natural numbers are just numbers that we use for counting, starting from one, going all the way up to what? Up to infinity. So then this is going to comprise of the listing that is 50, because we have less than or equal to on that part. Then we have 51, 52, 53, 54, 55, 56. Well, you can continue listing all the way up to 59, because 60 is not what? 60 is not part of it there because there's strictly less than symbol there. Right. So this is how we could list this set. On the other side, we have this set now, part B. They're telling us that B is a member of X is a member of the real numbers. So see this set B is equal to the set of OX. You see the first part, set of OX, such that that these two dots just means such that then X is a member of real numbers. So real numbers, just numbers that we can represent on the number line. I think you do remember what a number line is. So then, and they're giving us the other condition. The other condition is that X squared, X, so there's this, it's raised, so raised to the power 2. That is X squared minus 5X plus 6 is equal to what? To 0. So X is a real number, and this condition here that we've been given a quadratic equation. So meaning to get the listing, we have to find the roots of this quadratic equation, or we have to find the values, the two values, since it's quadratic, raised to the power 2, polynomial of 2. We have to find the two values which it will give us. So how do we do this? So to handle this quadratic equation, we just have to find, first of all, we can use, say, okay, I have my product, and product, remember the general form is ax squared plus bx plus c equal to 0. So I look at my a in this case is just 1, then I multiply 1 by my c. My c is that 6 there. So I'm multiplying that by 6. This gives me 6 like that. Then I get the middle part, which is my sum, this negative 5 here. I just get the way it is. So sum is always just b, so which is negative 5 in this case. Then I can look for my factors. So we can get the factors. So what are the factors that we have? So we're looking for a number that when we multiply, we get multiply the two numbers. We're looking for two numbers that when we multiply, we'll get positive 6. But when we add, we get negative what? Negative 6. What are those two numbers? What are those two numbers? Okay, so the two numbers that we're talking of, that is, you have negative, uh, so -3 and -2. So when we add these two, we get -5. When we multiply them, we're going to get a positive what? Positive 6. So now, from here, we are going to just replace there. So we have x squared, then minus 3x, then minus 2x, plus the 6 and equal to 0. So this is what I have in the first part. Then from here, okay, so from here then, let me erase this part so that we can use this part of the board. Okay, then we're going to have that I'll have x. So here I'm going to factor out. So I factor out this and I factor out that part there, this one like that. So I have x. Here what's common between the two is x. So I have x, then I remain with x minus what? Minus 3 there. Then on the other side, I factor out a -2. Since -2 is common, I can factor out a -2 there. Then I remain with x when I divide the first part. Then the second part I divide, I remain with negative what? 3 like that, equal to 0. Then this here, I group the x and the -2 there like that. Then I group x, I get one of these, x minus 3 equal to what? To 0, like that. So then here I'm going to equate to say x minus 2 equal to 0, or x minus 3 equal to what? To 0. Then I get x is equal to 2, or x is equal to what? To 3. So now here, answering or listing out my set B, since we are looking at listing. So listing means they've told me it's a set of all x such that x is a real number and x is defined by this equation. And we found that those two numbers, those two real numbers are just 2 and what? And 3. So x is comprised of 2 and 3, like that. Okay, I don't know if there's any questions thus far. Is there any question? Right, so there's no question, then we continue. Number 2 is we look at the kind of the opposite now. So the other one, we're looking at listing out. So tabular form is listing. Then now we look at another representation of sets which we are, which is by set builder notation. Set builder notation. So in this one, we usually have a listing given, then we have to write it in set builder notation. So this form here on top is what is set builder notation. So you have a form where you're describing what the set is. That's what it is, using these notations. So you, of course, so another thing that we can mention before we move further is that in this course, when representing a set, we said we're gonna use a capital letter. That's for a set. Then the elements inside the set, we use lowercase letters. Then when we're listing out or when we're trying to describe, we use these curly braces. So these are the ones that you see outside there. And then we use these other letters like X, and you see me writing natural numbers, you see me writing integers like that, and so on and so forth. So now what this means is I'm going to read this out. So this is set A is such that it's a set of OX such that, so the two dots here, so the here is just saying it's set of X, so meaning just X is representing any number right now. Set of OX such that, the two dots such that X is a natural number. It's a natural number, and natural numbers, we know the numbers from 1 to infinity, and X is less than what? Less than 7. Okay, is that a question? Is that a question? Okay, I guess it's not. So we continue. Then we're saying x is less than what? Less than 7. So when you look at this here, if we're to list down from what we are, just from looking at the roster form or the listing method, which we just looked at, listing out set A will just be, from there, it's natural number, it's less than 7. The numbers that are less, and it's strictly less than. So meaning 7 is not part of this listing. So I have 1, 2, 3, 4, 5, and 6. These are the natural numbers that are less than 7, according to what we have there. Now, we have been given these two examples here, and then they're telling us to write this in what set beta notation now. So how do we go about this? So to write this in set beta notation, we have set A, and then set A, they're telling us, when you look at what we have numbers from -1, -3, -2, 1, all the way up to what? Up to 3. So how do we write that? So we say, okay, so we say this is a set of OX such that X is you can say X is an integer, X is a real number, but X is an integer, of course. So X is an integer that is, so X is an integer, and or you could represent, you could use a comma, you could use and, whichever, and you're saying it lies in between -3 less than or equal to, so X is in between -3 and positive what? 3, like that. So this is how you write it out in what? In interval notation. Either you write it the other way around, like where you switch them, that is saying X such that, then you start with -3, X3, then you say X is an integer like that. Okay, whether you write it like this or the other way around, it's still correct. So here what we are saying is that our set A is a set of OX, meaning just element, just any arbitrarily what's this point or number, just any number in short. But then we've specified what that number is. We've said it's an integer. So now it has just moved from being any number to being an integer. So it's specific now, it's an integer. But also it's being specified more to say that, okay, this integer also is in between -3 and what? And 3. And I've put it strictly here, there's less than or equal to, and there's less than or equal to, meaning -3 and 3 are part of that set. So if somebody is able to see this, if you see this, meaning you would be able to what? To list, what you have to list down is what you have to list down is this here, is this set. So after saying that, oh, okay, it's an integer. So integers are just positive and negative versus natural numbers. Just negative and positive natural numbers, meaning the same ones, they are moving 1, 2, but then there is the -1, -2, and all that, and you would know. So now, from here, you would be able to what? To list down, since it's saying -3 to what? To 3, meaning you start from -3, -2, -1, 0, 1, 2, 3, and just like that. Then on the other part now, here, on the other part, there we have to also write this one. So let me erase this. Okay, so what are we writing for this one? So for this one, we look at how B is. Okay. All right, so, okay. I have some. So what we are saying about set-beta notation, I'll repeat this again. What we are saying is that it's a shorthand way of describing describing a set. So you see what this set is, right? I had to list down all the elements that are in that set, like from -1, -2, negative, all the way up to 3. I have to list down all those things. But what set-beta notation comes to do now is it's going to change that, and you write a shorthand way, a short way of going to represent that, but still mean the same thing. So how, or what we are saying is that this is the form first, which we have given. So this is more like the general format in which you're going to have it. To say you have your set, of course, A, then you're saying that this X is an element, meaning an element of that set. Then here, so it begins now, that shorthand way, you begin to describe the set in a shorthand form. So I describe what is in my set. So my set, there is this number or this element is a natural number, is what this is saying. So X is a member of N, meaning X is a natural number. But also this element that is in my set is less than what? Less than 7 is what this is given. So meaning somebody from this shorthand way could list or could use the other method, which the roster method, could list out the set. How from this description, natural numbers, they know, okay, natural numbers go from 1 to positive infinity. But then they've given another condition that, oh, they're actually less than what? Less than 7. So if I start listing out 1, 2, 3, 4, 5, and then 6, it's saying less than 7, meaning 7 is not part of that listing. So then you close here. So you see that I wrote, so this here, this set was written in this shorthand description here, which is the set beta notation. So that's what we are doing with these sets when it comes to writing in set beta what notation. So as we said for A, when you look at these numbers are integers. Since integers, when you look at integers, it's just positive and negative what? Negative natural numbers. That is, yeah, negative and positive natural numbers that are listed. So those are what? Those are integers. But now when you look at the integers, what else apart from these numbers being integers? I see that it does not compromise the whole set of integers, but of course it just comprises of integers that are in between -3 and what? And 3. So that's what I have to what? Indicate. So I'll say a set of OX such that these numbers here are integers. I put Z there, the Z like that stands for integers. And these numbers are just in between 3, so -3 less than or equal to X, and then less than or equal to what? To 3, like that. So this is what it means. So now, why the less than or equal to? So the equal to is because 3 is part of my set. And also, I mean -3. And also on the other side, 3 is part of what? Part of my set. That's why I have the equal to. If 3 and -3 were not part of my set, I would not have put them there. So somebody who writes this also, set of X such that X is an integer like that, and X is in between -4, less than X, less than 4, like this. This is actually the same thing, because here you're saying less than 4, like -4 is not part of it, and also the 4 there is not part of it. So when you list down, you would list down the same thing here. So somebody would write this or write that, they'll still be marked what correct, because you're describing the same set. I don't know if it's clear now. So interesting. Okay, the person that I don't know if right. Since there's no question, I guess we move. We do this last part here. So this here is saying we have B. So set B, when you look at set B, it has numbers -3, 6, 9, and 12. Those are the numbers that are there. So now, how do we get what are we going to do with these numbers? How are we going to write it in set beta notation? So I'll say it's a set of OX again, such that X is so what is X? So when you look at what I have here, I'm going 3, 6, 9, and 12. So in short, I'm going in multiples. What these are multiples of what? Of 3. So then if I have a 3 here and say I have n, n to just represent any number, which is going to be according to what this is, it's just going to be from 1 to 4. You will see why I say so is the first one. If n is 1, so if n is 1, we get that this is going to be 3. Since 3 minus 1 is 3, I mean multiplied by 1 is 3. Then 3, if n is 2, multiply this, here we get 6, which is the second number there. Then 3, multiply this by 3, we get 9, which is the third number there. 3 multiplied by 4, we get 12, which is the what? The fourth number there. So this here, in short, is what our set here we could use to describe our set. So we say that X is a set of all x such that x is a natural number. Since these 1, 2, 3, 4 are now just natural numbers, and what we're getting, these 3, 6, 9, and 8 are just natural numbers. So then we're saying x is a natural number, is a natural number. Then, okay, so natural number like that. Then when you look at also what x is, so x is equal to what? X is just equal to what? To 3n. So x is equal to what? To 3n. X is equal to 3n, because at first you see what's giving me these numbers is the 3n. What's giving me the 3, the 6, the 9, the what is the 3n. So x is just equal to 3n. Then you describe also the range for what, for the n. So now you're saying that this n, the n is just in between what? So n is just in between 1 and what, and 4. 1 and 4, because we put 1, 2, 3 up to 4 to get these numbers. So this is how it would look in set bit annotation. So if you want, you could have left out this part and just started it like b is equal to x is a member of natural numbers such that x is equal to 3n, 1 less than n less than 4, kind of the same thing like this. A shorter way, in fact, it's more cleaner, I think, and a shorter way of writing it than this first one. You could have written it like this also. So this is how you use set bidder notation, or this is how you'd write from the listing to set bidder notation. I don't know if there's any question here. Okay, there's no question. So just another thing that we will describe or we look at is a singleton set. So a singleton set is just a set that has one element. So if I have A, it has the element A inside, meaning that's a singleton set. To be called a singleton set. Then also another concept that's very important is looking at what an empty set is. So an empty set, or it's also known as a null set or void set, is just a set that has no elements in it. So we represent it by curly brackets with nothing there, or we just write this O and cross it like that. Then this would mean that it's an empty set. It has no elements. So by definition, so this is how it would look. And there's nothing here, so it's empty. The last other key concept we look at for today is a subset. So a subset, we're just saying if we have two sets, we have A and we have a set B. If we have these two sets, A and B, then we're saying that A is going to be a subset of B, which would denote A being a subset of B like this. If every element of A is in B, if every element that is in here is also in here, then we say that this here is going to be a subset of B. In short, A is going to be, if A is contained in B, then A is a subset of B, is what we're saying. So example here, we have this set A has 2, 4, 6. Then set B has 1, 2, 3, 4, 5, up to 6. So now, A here, you see that the 2 belongs there, the 4 also is there, and the 6 is there. So A qualifies to be a subset of what? Of B, because every set that is in A also belongs to what? To B. On this other part though, that's not the case, because we have A to be 1, 3, and 5. Then here we have B to be 1, 2, 3, and 4. Then when we look at these sets here, of course, the element 1, 2, and 3, I mean 1 and 3, 1 and 3 are also in B, but then 5 is not in B. So since 5 is not in B, but it is in A, of course, but it's not in B. So this A cannot qualify to be what? To be called a subset of what? Of B. Yeah, cannot qualify to be called a subset of B. Okay, so I don't know if there are any questions, but we like to leave it here for today. when we come in the next class, we pick up on these concepts where we come and just look at questions, um, questions on how you would list, on how you would you'd put them in tabular form, even as we build on other concepts. I don't know if there are any questions. All right, so as I said that at the end of this, I'm going to show you also how to access the website. So, okay, let me do that. Okay, so I hope you're able to see my screen. So you just go in your browser. I always type it so you can see that it's here, discretelearning.com. And then you click that. See the first link that comes. There is going to be Discrete Learning Institute. Then you open that. So after opening that, you find this home page coming in here. Then you can go to say subscribe to course or start learning. So if you've not registered for any course, you click there. Okay, let me just load. It will bring you this option here. So if you have an account, you sign in your account. If you do not have, you can go create an account, make an account, and then you can log in. And then now, after logging in, you have these. Oh,